Okay, I'm making this video to address some of the points you, Gary, have made on your DraftScience channel. I will be talking about what Newton actually said, or at least what is the correct interpretation of Newton's second law, something about guns and bullets, and finally something about acceleration and fuel consumption. The goal of this video is not to convince anyone that this is the way the physical reality is actually working, but just to increase some understanding of the kinetic energy, both my own understanding and hopefully others as well, and to give some perspective, mostly from the point of view of conventional physics. So yeah, I would be really interested in hearing your thoughts about this video, Gary. Let's start with Newton's second law. The conventional definition, or definitions, that you often find in textbooks, for example, is either force equals to mass times acceleration, or force equals to the rate of change in momentum, meaning the change in momentum divided by the change in time. These two here are of course the same. To see why this is the case, let's first write this in a simpler form. So we get the change in mv divided by change in t. And as we can assume that the mass of the object is not changing, we can take this m outside the thing that is changing. So we get m times the change in v divided by change in t. And this object here is of course the same as acceleration. It's the rate of change in velocity. If you have high acceleration, it means that there's a large difference in velocity within some unit of time. And according to you, what Newton was actually saying is that if you want to go twice the velocity, you need to apply twice the force. And I guess that your argument is that this is somehow incompatible with this equation here. So let's take a closer look at that. First, let's assume that the mass is not changing. So now it's quite easy to see that if we double the force, we are also doubling the acceleration. And let's also take a look at what this means in terms of velocity. So here we have two objects with the same mass. To this object here, we are applying twice the force and thus giving it twice the acceleration. And we are also assuming that both of these objects start at rest with zero velocity. And now it's quite easy to see that at each point in time, this object, where twice the force was applied, has twice the velocity. So in this sense, you were correct about what Newton was saying. If you want to go twice the velocity, you really do need to apply twice the force. Of course, assuming that the duration of the force is the same, because you could also apply the force, maybe the equal force, for just a longer period of time to gain more velocity. But if the duration is the same, then you need to apply twice the force to gain twice the velocity. And this F equals ma is just another way of saying that, whether or not Newton ever used the word acceleration. Okay, then something about guns and bullets. Several times you've made the argument or thought experiment where we have a gun with relatively high mass, a bullet with relatively low mass, and an explosion applying equal amounts of force both to the gun and to the bullet. And the question is, how is it possible that the bullet gains so much more kinetic energy? Let's say the bullet gains 1000 joules when the gun gains only 10 joules, even though the force was the same. Now, a simple answer one might give you is that when looking at the definition of kinetic energy, it doesn't depend only on the force applied. The force alone doesn't determine the kinetic energy, but this perhaps isn't explaining anything. So I have this thought experiment that hopefully would give some intuition, give some intuitive understanding on how the bullet gains more kinetic energy. So here we have the barrel of the gun. This is the bullet. And just to make the visualization easier, instead of an explosion, let's use a spring, a compressed spring as energy. So when the gun is fired, the spring is released. It is pushing both the gun and the bullet with equal amounts of force. And as the bullet has lower mass, it accelerates easier. I hope you, Gary, also agree with this. So when the bullet travels some distance, the gun travels only a tiny bit to the opposite direction. And let's also decompress this spring like this. Yeah. And now it's quite easy to see that most of the spring was actually moving towards the bullet, to the direction of the bullet, whereas only a tiny bit of the spring was moving to the direction of the gun. So there's clearly some kind of imbalance, asymmetry in the way the force was applied to these objects. So this might already suggest why the bullet gains more kinetic energy, or at least give some kind of intuitive idea about this. But what I think is also quite interesting is to think about what happens if we rewind this scenario. So what happens if we make things go backwards? So we have this bullet with its final velocity gained from the spring. It's now traveling towards the spring. And doing so, it pushes the spring, it's compressing the spring further and further. Also the gun is doing some compression, but to a lesser degree, just a tiny bit. But the bullet is doing most of the compression work. And doesn't this fit quite nicely with the idea of kinetic energy? At least I think that kind of the core idea of kinetic energy is that objects with higher kinetic energy can travel further against some opposing force, against some kind of pressure, assuming they don't bounce or explode or anything like that. And actually this is also an answer to the question, why don't they use bullets to take down buildings? When you shoot a bullet towards a building, what happens to the bullet is that it either just explodes, or it bounces, or it drills a small hole to the material of the building, which really isn't useful when trying to take down the whole building. And that's why they are using these heavy wrecking balls instead, even though the kinetic energy might be lower. But the wrecking balls are more suitable for the job. Another similar example might be that if you have a person running towards you and you want to stop that person, you might take a small particle, very small particle, shoot it with very high velocity. The particle might, for example, penetrate the cell of that person, maybe cause some DNA damage or something like that. So the kinetic energy of the particle would go into breaking some chemical bonds. Even though lots of energy was used, it wasn't really useful in stopping that person. But you could also take a stone, heavy stone, throw it to the face of that person, and even though the kinetic energy might be lower, it probably is still more suitable for the job, for stopping that person. Okay. You also had this extension to this thought experiment where we have two guns facing each other and two bullets in this, what you call a zip gun, I guess. So basically a tube, two bullets, and an explosion in between them. And I guess your understanding here is that since the gun in the first scenario gained only 10 joules of kinetic energy, now both of these guns would gain 10 joules or 20 joules in total. And the bullets here would gain 2000 joules of kinetic energy in total, even though the explosion was the same. So obviously there seems to be some kind of contradiction. And I also think that obviously this is not what would happen, especially if we are assuming an ideal explosion, so all the energy of the explosion goes into moving these objects. Then the kinetic energy of the guns equals to the kinetic energy of the bullets, meaning that the guns here would gain more velocity than the gun in the first scenario, basically because there's no light object here stealing the kinetic energy and allowing the explosion to spread out into one direction. And the bullets here would gain less velocity than the bullet in the first scenario, basically because there's no heavy object here redirecting the explosion to the direction of the bullet. So, at least to me, this is quite intuitive and I don't see any contradictions here. Then we'll talk about acceleration and fuel consumption. So you have made the point that according to kinetic energy theory, you would need 4 times the fuel to gain twice the velocity. And you also say that this never happens, this is not reality. And I would say that you are partly correct here. It depends on the method you are using to accelerate. When it comes to acceleration, there are basically rockets and cars. So what rockets do is that they use the chemical energy of the fuel to push out part of the fuel mass into the opposite direction, and thus giving the rocket some thrust. Whereas cars, they use the chemical energy of the fuel to push against some immovable object. So the tires push against the road, and the road isn't moving anywhere, practically speaking. And I would argue that the fuel consumption between these two methods is different. And let's take a look at why that might be the case. So here we have a rocket in space outside of gravity. Let's say it has a mass of 10 and it starts at rest with 0 velocity. Then it shoots out some unit of fuel with a mass of 1 and a velocity of 10. I put a minus here just to emphasize that the direction is opposite from the point of view of the rocket, but that really isn't that important. What is important that the rocket gave this unit of fuel some change in momentum, and thus the rocket also gained the same change in momentum to the opposite direction. So it gained 1 velocity. Note that here I'm not taking into account the loss of mass of the total rocket. So the total mass of the rocket is the rocket itself, but also the fuel that it's carrying. And now it's shooting some of the fuel out, so there would be a decrease in mass, but just to keep these numbers simple and keep the math simple, I'm not going to take that into account, but let's get back to that in a moment. Next, the rocket shoots out another unit of fuel, again with the mass of 1, and as the change in momentum is still the same as with the first unit of fuel, this unit of fuel has a velocity of 9, because it was initially traveling with a velocity of 1 to the direction of the rocket. But still, the rocket gains the same change in momentum to the opposite direction, so now it's traveling with a velocity of 2. So, based on this, doubling or using twice the fuel would lead to twice the velocity. And if we took into account the loss in mass of the total rocket, the rocket and the fuel it's carrying, we would see that acceleration would become easier, and thus twice the fuel would actually lead to a bit more than twice the velocity. But things are a bit different when the object is pushing itself against some immovable object. So here we have a thought experiment where we have 2 immovable walls with some springs attached. And here's our object, our ball that we are going to accelerate. So let's load our ball. and let the first spring decompress, giving the ball some acceleration. And here we engineer the experiment somehow that the ball can pass through the second wall, and just when it's in front of the second spring, we let the second spring decompress, giving the ball some additional acceleration. And the question here is, do you think that both of these springs gave equal amounts of acceleration to the ball? Was the change in velocity the same with both of these springs? Because that would certainly indicate that twice the fuel, or twice the spring energy in this case, would lead to twice the velocity. Now, I don't think that's the case. What I think would happen is that both of these springs would apply equal amount of force to the ball. So the push would be the same in terms of force. And what would happen with the second spring is that as the ball is already moving here, it already has some velocity, the second spring decompresses faster. And so it applies the same force, but for a shorter period of time. And at least to me, that means less acceleration based on the Newton's second law. And I did some calculations. I'm not showing the equations here because they are a bit messy. Maybe I'll put them in the description or something like that. But based on my calculations, if we have a spring that accelerates the ball from 0 to 1 velocity, you would need in total 4 of these springs to achieve the velocity of square root of 4, which is 2, which is twice the velocity in comparison to just one spring. So here in the calculations, I just assumed that each spring applies the same amount of force to the ball, but the duration of the force is shorter because of the higher velocity at each spring. And of course, this is perfectly in line with the kinetic energy theory. So yeah, that was it. Would really like to hear your thoughts about this, and from other people as well, if I'm misunderstanding something or making some mistake. Okay.